Hello everyone, I'm Dave Brubaker. I'm the product line manager for Zynq UltraScale RFSoC at Zyng. So I'm going to be talking today about the RFSoC. And also presenting with me is going to be Vincent Mui, and he's over there. He's going to cover the second half. So if we look at the agenda today, I'm going to talk a little bit about on the overview of the RFSoC. For not everybody knows about what the RFSoC is. So I'll give you a little background. I'll give you a look at what our device is doing, what we call the Gen 3 device. And then Vincent's going to take it over, or I'm going to talk a little bit about boards and tools. So it's a new section that I would like to educate you on. Then Vincent will take over frequency planning, because if you're making any kind of a radio system, frequency planning is extremely important. And it's a little bit tricky. So there's some frequency planning tools we have online. He'll review those. And then the other thing we'll talk about is one of the key advantages to RF sampling converters is that you can do a lot of the filtering in the digital domain and have it reprogrammed. So that's a feature we have. And so we'll talk about what we call multiband support. Okay? So we'll go ahead and get going. For those of you, as a background, you may have seen this, you may have not seen it, but essentially the Zynq UltraScale plus RFSoC is a Zynq UltraScale MPSoC with two key IPs. The two key IPs are the RF sampling data converters, the ADC and the DAC, and then the SD-FEC block. The SD-FEC block is a soft decision forward error correction block. It's hardened core and supports the 5G new radio LDPC standards. It supports turbo for 4G. It also supports the DOCSIS standards. So in any communication system, when you transmit a signal either over the air or over a cable, there'll be errors. And so we put known signals and known bits in there so we can correct those errors. Now, typically, a hardcore SD-FEC is saves about 80% of the power if you were to implement a soft core. And so it's quite a powerful core. I don't have a lot of data in this one, but if you're interested in that, then you can take a look at it on our website. I'm going to talk a little bit about the RF ADCs and DACs, but again, relatively little performance or little data because we've covered that before. So if you look at around the world, we have the quad A53s and the dual R5s. We have our standard hardened engines, our 33 gig capable transceivers, and our standard programmable logic that would be available in the Zynq UltraScale Plus family. But this particular part is very DSP heavy. We have 4,700 odd DSP slices, which is quite a number relative to the system logic cells. So there's a variety of customers who just use this part without the data converter strictly because the number of DSP slices. Okay, so go on. Now, it's interesting, about 2017, the first Zynq UltraScale RFSoC was announced. It's called Generation 1 now. It had an input and output bandwidth of the data converters of 4 gigahertz. So you can operate anywhere from DC to 4 gigahertz on that particular part. It actually comes in an 8x8 or 16x16 configuration of DACs and ADCs. And what we do is we time interleave 2 ADCs to get to we time interleave them, we're at 4 gigasamples in an 8x8 configuration. And then if you run the 16x16 configuration, you get nominally 2 gigasample on the ADC. The DACs in this particular part run in any configuration at 6.55 gigasamples per second. Now it's interesting, this part was announced in 2017, as I said. It went to full production in 2018. And, back 4 years ago, nobody used the word analog and Xilinx in the same sentence at any time, right? But now we've got this RF sampling data converter. The truth is that Xilinx had been working on this IP since 2012, developing a number of products and test chips. And once the IP was validated, it was actually then ported to the standard 16 nanometer MPSoC product family. And that's what enabled it to come out pretty quickly. It is a monolithic device. It integrates, on the same chip that's dissipating, quite a bit of digital switching noise, these very sensitive RF sampling data converters, which the noise spectral density of the device is in the minus 150 to minus 155 dBm per root hertz. So very comparable to any tier 1 RF sampling data converter. And it's quite an effort to maintain the isolation. But that part's out, and it's very successful. So we went ahead and announced Gen 2 and Gen 3. These were both announced in February of this year at Mobile World Congress. Gen 2 is already released and fully shipping in production today. It's a minor shift of the Gen 1 by moving the input and output bandwidth to 5 gigahertz. It's only available in a 16 by 16 configuration, and it's really aimed right at the 5G new radio bands in Asia for massive MIMO applications, okay? So the Gen 3, we'll talk a little bit more about that. That's actually been in development for a little over a year, maybe 2 years at this point, and upgrades the analog mixed signal block, the AMS block as I'll refer to it, is where the RF DACs and ADCs are. There's a lot of new features in that, and we pushed the input-output bandwidth to 6 gigahertz. At the same time, we've increased the maximum ADC sample rate to 5 gigasample. That's a 25% increase over the 4 gigasample that's available in the Gen 1 device. And then the DAC itself can now go to 10 gigasample. So and there's also several new features in there that add additional hard IP within the AMS block. Now, when I talk about the AMS block, it's not just a data converter. It has a complex mixer. It has hardened digital up conversion, digital down conversion. So it's a whole DFE. So you can make use of that in the system. Now, we also announced, I got to watch these buttons because there are 2 green ones here. Last year at actually XDF, we announced the Versal platform. Now, Versal platform is a 7 nanometer process. So, you know, in Xilinx, what we do is we have a process node, we develop IP, we build a whole family of products among this process node, and the last one was the 16 nanometer, which includes all the Zynq UltraScale Plus devices, and that's all these particular parts here. But now we're moving to 7 nanometer, and there's several families with that particular Versal product line, and one of them they talked about is what we call AI RF. So we are planning on the AI RF. We do fully plan to have RF sampling converters and a 7 nanometer product with what we call the AI engines, or the AI engines that can be used to do a lot of DFE functions at about half the power that it would take to do them in programmable logic. So that part is in planning. We don't have a firm date, but you know, stay tuned and we'll have that pretty soon. Okay. Since we are at a kind of an update show, I wanted to show you some data, and we have a demo out there on our Zynq UltraScale RFSoC Gen 3. It's a quick update. The part has actually only been back from fab, you know, roughly about 5 weeks now, and we started testing, and the results are actually quite good. I'm going to show you this board here. I'll talk about it first. This is actually what we would consider an evaluation board, and there's a board we shipped today called the ZCU 216. I mean the ZCU 111. That's for the Gen 1. I'll talk about that in a minute. This is actually the ZCU 216 board. So this board is what we would ship if you wanted to buy an evaluation platform to evaluate the device. Don't let the kind of Frankenstein cables and stuff scare you here, but it's actually pretty good platform. So we actually have 2 platforms. This is what we would call our customer eval platform. We also have a characterization board. It's larger. It doesn't have DDR. It's very limited on the clocking, but it's something we use to test the part and characterize it. So we actually had tested both of these boards. What we're showing here is the ACLR of 100 megahertz wide signal, 256 QAM, transmitting it at roughly 6 gigahertz, like 5.99 gigahertz, and we're achieving about minus 65 dBc ACLR. Now that's running roughly about 2 to 3 dB backed off from full scale. Full scale output of the DAC is about 4 dBm, and so it's pretty high output power, and that's of course the peak power, because that waveform probably has, I don't know exactly, but probably around 10 or 12 dB peak to average power. And the typical system requirement in a wireless system is minus 45. So this performance is really quite good and doesn't limit an overall system performance at all. The other thing I'm showing is the EVM. That's the error vector magnitude. And in this case, we're measuring an error vector magnitude of about 0.4%. In this case, the DAC is sampling at about 6 gigasample. The demo we have out there is sampling at 10 gigasample, so the EVM is degraded to about 0.7% with the higher sample rate. So these are actually really outstanding data. You can see the constellation here. And I'd encourage you to go take a look. We're actually quite happy with the results right now. The results are looking very good. Our original intent was actually to show our characterization board because it was received earlier, but we only got this board back about 2 weeks ago and we have it up and running. And is working pretty well. So this actually is, can you hear me? Okay. So we actually have the part here, the RFSoC. We have a clock module. It's called a Clock 104. And it's a plug-in card. And when you look at how somebody would use the system, there's a lot of variation in how they want to do it. Sometimes they want to use an external sampling RF clock. They want to use a reference clock. And this allows you to do all of those configurations. And it's kind of a plug-in board. And then we actually bring the RF signals out via an FMC type connector, which actually works to 6 gigahertz. And then we have a daughter card we plug on it. It's the same concept we use for the ZCU111. And this particular board, you can actually bring out all 16 DACs and 16 ADCs via these little connectors right here. They're called Carlisle connectors, and then they're cables. So you can actually bring them out, and then they're differential, so you can then run them back into balance or do whatever you want to do. Very convenient. So depending on what your use case is, you can change what it is. So the summary is we're very happy with the performance. We're going to be sampling this part in December, what we call ES1 samples. They're a certain level of qualification through our test program. They'll go to full production in August of 2020. And this board will be available for customer shipments in February of this year. That's when the first time you can order the board and get it. So we're real happy with the progress there. So now I want to talk a little bit about overall boards and tools, because if you're a user, you're going to get some sort of a board, and then you're going to want to build a project, and how do you do that? And if you go look on our website, we have a lot of different tools, and it's actually quite confusing just to anybody who's not used to it. And so I thought I would cover it. So there's a variety of boards available for the Gen 1 and the Gen 2. I mentioned this ZCU111. It's a very large quantity of boards we've shipped for that. I think it's the second highest board runner at Xilinx, and it's only been in production for a little over a year. And so it's basically, like I mentioned, it's an 8x8 configuration, not a 16x16, and we have breakout cards. And so that's available. I'm going to skip the next one and come back to it. We have what we call, would be our characterization board. It's a ZCU1275. It's the only way to measure Gen 1 on a 16x16 configuration. The Gen 2, again, likewise is available on a 16x16 configuration, and kind of like a characterization kit. And what board you get is important because the software you get that works on different boards. So it's a little bit of a challenge depending on what's available and what you want to do. What was just announced, and we did do a press push on it, is a part that Avnet released. They took our ZCU111 and then they added a daughter card that actually has a Qorvo RF front end on it. So now you've got RF in the LNA, there's step attenuators and gain control, and they've built a whole GUI and stuff around it on MATLAB. So I'll talk a little bit about that. So that's actually available now. And you can do RF over-the-air testing with this particular card. And so one of the advantages of this concept is that you can take our main board and then build your own daughter card and hook it up and do your own characterization. And we do offer the schematics and so forth if you want to look at that. Now, on the Gen 3, we're planning to do 2 evaluation kits. Okay, one is going to be the 8x8 like the ZCU111, and the other is going to be a 16x16, which brings out everything. So they're called the ZCU208 and the 216, respectively, for the 8x8 and the 16x16. Okay, so I've shown you the 216 board. We're leading with that. The 208 will be available roughly in March of next year. Okay, so now, which tool to use? Okay, you get your board, and what do you do? Okay, so it turns out there's a lot of different options. We have something called the RF evaluation tool. It's advertised. You can download it off the web. We have a tool called the RF analyzer. You can download that off the web. Avnet has a product they've now released called RF Explorer. That comes with the, actually the Explorer tool itself is free, but you can get that with their card and their development kit. Within Xilinx, we have Model Composer, System Generator, which are tools that you may be familiar with. There's actually a tool that very few of you have ever heard of that's available from MATLAB that is targeted for the RFSoC. And there's this new thing called starter designs, and I'm going to spend a little more time on that today. The starter designs are simple hardware designs that if you're an FPGA engineer and you approach it from that perspective and you want to put something together and have it work pretty quickly, it's probably the best way to go. It's kind of a grassroots effort, so it's not something that has got a lot of traction and offering at Xilinx. We can give you the designs, but it's a little bit you're on your own. But I'll go over what's in it, and if you're really pretty capable with an FPGA, it's a really good way to get started and not have to go through all the Linux and software development you might have to in some of the other ways. So the answer to this question is, okay, it kind of depends who you are and what do you want to do. It makes sense, right? Who are you and what do you want to do? So we have a type of persona, we'll call them different personalities. You just want to do a demo. I just want to see whether this RFSoC has enough performance and we can characterize it. Okay, so that's one type of a persona. Then if you really think about it, you've got these whole algorithm engineers that do system level development. They might be using channel fading and they want to look at stuff. So they're like algorithm engineers. And they work in MATLAB and C, and they have no idea what a bit file is, but eventually you've got to get this thing into hardware and have it work. And you've also got the person who's like an FPGA engineer, and in the end, they're the ones who have to put everything on an FPGA, close timing, and make it work. Okay, so you've got all these different personalities that you have to deal with. And we kind of break it into these kind of personalities. You've got the comms engineer, and I've talked about it. They're typically familiar with MATLAB, but not really sure how to even make a bit file, open up in Vivado and target a device and all that. You've got the RF engineer, and they're really worried about RF design, okay? And they're worried about, does it meet the performance? They want to characterize it over a variety of situations. And they are not really used to turning on an FPGA and making it work. And so they're certainly not used to bringing up Linux and having to deal with that. And so they're used to basically plugging in a USB onto their PC, having a GUI pop up from TI or ADI and programming the part and have it work. Okay, it's pretty convenient. Okay, so you've got that's another type of persona. And you've got the FPGA hardware engineer. And, traditionally the FPGA guy's in a different building, and the only way he knows about RF is through this thing called JESD, right? So what does noise spectral density mean to me, right? So that's another person. And and then there's the test and verification engineer, somebody who actually builds it work. So this product is extremely complicated because it spans a variety of people, and how do you satisfy everybody? And it's a difficult problem. So I'm going to talk a little bit about which tool works for best each person a little bit. And you can start by, okay, it kind of has a flow. You look at the workflow. You start by maybe doing a demo, and then if you're really doing an algorithm, you're going to model. You'll have some sort of a golden model that you've developed in C or MATLAB, and then you might actually want to do simulation, algorithm development, algorithm refinement, and then what you're going to end up doing is say, okay, I've got this thing in software essentially, and I need to target it into hardware code or something that goes there. And so there's like a code generation. And there's really two types of code generation. There's the hardware code that goes on the PL, and then there's the programmable logic, and then there can be firmware or software that goes on the A53. And they can be interrelated. So how do you generate that code? Okay, so we'll call that the PS code. And then you're going to basically build something, and there's two types of simulation that people do. There's what we call hardware co-simulation or FPGA in the loop. So you'll basically build something, program it on the FPGA. You'll run something on the computer or MATLAB. You'll run it through the FPGA and see if it works. But you also have now what we call RF in the loop or analog in the loop. So it's called data I/O by some people. So now I've got something that doesn't have to be necessarily all on the FPGA. Some of it can still be in MATLAB or on a PC, but I want to transmit something over the air and see what the air interface does to it. So that's another kind of prototype and test world. And then eventually the implementation and so forth. So you've got this whole process flow. In the end, you start off, is this going to work? And in the end, you're shipping things in production. And the personas come in and come out as you go through it. So, this is the different people. So I'm going to talk about each tool a little bit. I'm going to go maybe a little quickly. And honestly, this is way too shallow for anybody who's got a lot of questions on it. There's a lot of information online if you have additional questions on some of this. So the RF data converter evaluation tool, it's a great tool. It's targeted at the ZU+111. It's LabVIEW based. You don't have to have LabVIEW because we build it on LabVIEW, but it's based upon that. And it's really a great tool to do kind of a measurement of the DAC and the ADC and what they can do. You can actually store files in DDR, your own files. We have a variety of files. You can put them in and play them. You can sample them back and loop back and then do an FFT. and see what the system's doing. So you can measure a DAC and ADC performance in cascade and look at it. You don't know whether the performance is limited by the ADC or the DAC, but you can loop that back without even having a spectrum analyzer. So it's a great tool, and we offer that, and it's available. And I'm going to say that's the best tool for a demo on a ZCU111. But if you're going from that point to now I want to build hardware, it kind of becomes a difficult transition because it's very GUI based. Now let's take a look at what we call the RF analyzer. So the best way to think about this, if you're familiar with FPGAs, we have a tool called iBERT. And this is for our transceivers, and it allows you to measure like the eye opening of the transceivers, okay? So RF analyzer is board independent. That means it doesn't have to be on the ZCU111. It can be on the, your own customer board, and you program it in. It uses all the resources of the FPGA. You can now, still kind of based on GUI, bring up the DAC and the ADC and see if the customer board's working and debug the analog stuff without having any other tool involved. So it's a great tool for that, and consequently, I'm going to say it's the best tool to debug a customer board. You can do other things with it, but that's ideally what it's there for. And again, that can be downloaded from Xilinx.com. Okay. So I'm going to talk a little bit about the Avnet RF Explorer with MATLAB. It's a different tool. It was totally developed by Avnet independently. And, as a plug for them, they got this Quovo card. You can actually buy the Quovo card separately if you have a ZCU111. You can just get it and plug it in. But one of the things about the RF Explorer, and the Explorer tool itself is, I believe, free. It's actually built on MATLAB and Simulink, and it's native on their interface. And so it's very easy for you to take and stream data, and they have all the programmable settings set in for our data converter, so you can set the different things. You can actually set the interpolation, the decimation, and they actually have the filters mapped in there so you can see what will happen. And it's a great tool if you have data and want to run it out through the air and do some sort of a test. One of the examples we talk about is if you want to do some algorithm development like AGC loops and things like that, this is a great tool for that. Okay, and since it's built fully on MATLAB and Simulink, there's a lot of capability native in that tool natively. You can use the 5G toolbox to get 5G waveforms right out and run it and so forth. And we talk about this as being data I/O or analog in the loop kind of testing. Okay, so in the end, it's the best tool for analog algorithm exploration. So if you want to do that and especially with RF in the loop, it's a great tool for that. Now, I'm going to talk a little bit about Model Composer and System Generator now. They're both kind of different tools. They're available from Xilinx, but they're really not targeted to the RFSoC, nor are they actually targeted to the 111 board uniquely. But if you want to build some sort of a tool or algorithm in the Xilinx world, and again, they're built on MATLAB and Simulink, so they'll run into Simulink, and they're kind of optimized a little bit for the Xilinx devices and stuff. But these are ways you can actually take a design, build it up, and then eventually get a way to target it via Vivado to the device you're working on. But recognize there's nothing unique in this particular tool about the RF data converter section. That's actually a roadmap item, and hopefully we'll have that in the next year or so, but it's not available now. And the same thing kind of goes for the system generator. Instead of being a high-level tool, you can actually have RTL optimized blocks, particularly for the DSP. Again, so you can actually implement it. It's bit level and cycle level accurate. And again, this tool can be used to do some sort of a system development. Again, nothing to do with the RF data converter, but if you're doing a filter or some sort of other system or within the FPGA, you can use that. Okay, I'm going to have to hurry up here. Okay, so the other tool I want to give a plug to, you can go out and see the MATLAB. They have a demo of this. It's not widely promoted, but it's basically a tool that MATLAB did, and it actually works with the ZCU111, so it's targeted to that. And you can build a model in MATLAB, and then actually the best part is that it will actually target some of the code for the programmable arms and actually target the code for the programmable logic, hooks up all the AXI buses, and you can actually do a demo quite quickly with this particular tool. And so the advantage is from your model, you can actually have software and hardware code, okay? Now, it's not available, from a download, but you have to send an email to this account here, rfsoc@mathworks, and then they can provide those tools to you. It's really the best tool from end to end. If you want to start with algorithm and then get all the way to the end, it's a great tool. Okay, I'm going to talk a little bit about starter designs. These are new, like I said, grassroots effort, and it kind of grew out of people trying to build a design, without getting into all the Linux and building up all the stuff. So eventually you're going to have to come up with something like this, which is a hardware design in Vivado, and you're going to have to target it to the device, okay? So what these are designs. They're simple designs. They're very minimal, and they have step-by-step instructions on how to actually put it together. So if you're an FPGA engineer and you want to build something that includes the data converter, and you don't want to really get into the programming and so forth, this is a great way to go. A couple of things. It uses the ZCU111 board, okay? It is bare metal. It does not use Linux. Okay, what we provide is starter design, the project file with instructions. If you follow the step-by-step instructions, you can build this thing up and run the demo. And then from that, you see how things are hooked up. And if you want to modify it, you're free to do it on your own. Okay. I'm going to give thanks to John Lance and John McDougall who developed these, and they're really supported by the local FAE. So if you want these, you can contact myself, and I can send you the archives, and then you can play with them. But they're really kind of a grassroots thing we want to put out there. Again, it's not something that is set up to provide a lot of support, direct factory support. There's 4 designs available right now. We have kind of a send something in, get it back out design. We have, you can load something in a buffer, transmit it out of a DAC. You can do a loop back and see it in the ADC. There's also what we call MTS, or multi-tile sync, the ability to sync all the DACs and the ADC channels. There's 2 designs, one running at 1.47 gigasamples per second, and then one running at 3.93 gigasamples per second. Now, this is actually on the ZCU111, so when you look at multi-tile sync, that board limits the number of channels you can do MTS to, because we have high frequency and low frequency balance, but MTS has to all be at the same frequency and matched phase lengths. So it can be done. This is kind of a picture of the basic block diagram. And if you run through it, you'll get yourself 2 DACs and 2 ADCs all synced up and phase line. If you work through the steps, you'll see that they're not phase aligned or synced at the start off, and then after you run through this example, they are. Once you have this up and running, then you can add what other stuff you want to do into it and use it. So they're available, and if you want them, you can come up to me and I'll give you my card and we'll find a way to get them to you, okay? So lastly, I put together a spreadsheet, a graph, and I'm sure that this is the type of thing that was really hard to do, and everybody will argue with whatever check mark is there. And it all depends on your definition and all sorts of stuff. But pretty much there's a basic step you're going to be in the process, and then there's all the tools here. And I've listed, where it's really good, okay, things can be done really well, and where it's not so good or not even possible, and then average, okay. So like I mentioned, the evaluation tools are great for demo. It can't do really any code generation or any digital in the loop. That has to be done with other tools. And then, as I said, the MATLAB tool actually does quite a bit of this, okay? If you're doing the debug, the RF Analyzer is the best tool. And these starter designs, I list them here. They're very good. You can do a demo. They do PL and PS because we actually provide the code to you, okay? But it's not automatic. You don't have an algorithm to generate it. So there's a little star there. But it also is quite easy to do a hardware instantiation. So if you're at that back end and you want to bring up some hardware, and you want to do something specific, this is a really good tool to use. Okay, now we want to save the questions till the end so we can get through it. I've run a little bit long, so I'm going to hand it over to Vincent, and he's going to talk about our frequency planning tools and multiband.
Okay, thank you. Thank you, David. Hi, morning, everyone. I'm technical marketing for the RFSoC. Today, I'm going to present the frequency planning and multiband for the design and methodologies. If you have any questions, please weigh up, we can discuss. So first of all, we would like to review the RF system architecture. First of all, the signal coming in to the antenna and then going through the LNA, down converting, and then bandpass filter, and then down convert a few megahertz to the ADC. and then using the JST204B interface to connect the data converter and FPGA. The power efficiency is good, but it's only for the specific like frequency and bandwidth. So you can optimize your like passive component to optimize your performance. And then next, the analog data converter IC vendor, they introduced the RF direct data converter. So the signal directly coming through from the antenna and then directly sampling on the ADC, and then all the down converting, put it behind the ADC like the NCO decimations. So we move all the analog implementation to the DSP, and then it still need the JST204B to communicate between the RF direct sampling, data converter, and FPGA. So in 2017, Zynq want to do the enable the software-defined radio. We just want to processing all the analog data and then the digital data in the single chip. So Zynq include the RF data converter integrated in our FPGA. So there is a few value propositions. The first one is the lower power, small footprint, faster design cycle, and the flexibility of the digital domain. Because we can like play around the NCO and decimations in the digital processing. Here is the comparison between the traditional RF superhybridized and the software-defined radio implement with our RFSoC. For the traditional RF system architecture, we need two identical DAC for the in-phase signal and the contiguous signal, and then combine the IQ modulator to do the up convert. So we have a lot of analog discrete component on the system. Now, you can see the bottom line, and then our RF DAC, we have integrated two IQ NCO, and then the decimation, interpolations processing. So you don't need to like duplicate the whole analog signal to implement IQ. You only need one DAC to implement all IQ signal inside our chip for each channel. And then our chip has 8x8 and 16x16 channel. And then at the front end, and then we can like come up the frequency and then VGA and PA going up. For the ADC wise, we have like the similar for the traditional architecture. We need the identical ADC and ADC for I and Q. And then we just simplify with our RFSoC. One thing, we don't need the JST204B interface because we integrate everything, data converter and digital processing inside our chips. JST204B is not good for the power and limited bandwidth. So if you combine many channels with the single JST204B, you limited your useful bandwidth. That is not good for your 5G or A&D and test and measurement, because like the 5G, for the millimeter wave, you need up to 400 megahertz bandwidth. So that will be limited your millimeter wave implementations with the JST204B. Before talking about the frequency panning, we need to recap the concept of sampling. First of all, the Nyquist theory is more important when we dealing with the RF sampling data converter. So the sampling clock has to be 2 times bigger than your signal bandwidth, not your carrier frequency. Bandwidth mean 200 megahertz bandwidth or 400 megahertz. It's not talking about like 2.4 gig or 5 gig. And then for the like right-hand corner, we have like 3 diagrams. The first one is the sampling clock is much greater than the 2 bandwidth. So you can see the spectrum in between. It has a lot of space. You don't overlap each other. When your sampling clock is exact like 2 times of your bandwidth, you like close to touch each other, but it's still okay. And then if your sampling clock is much less than 2 bandwidth, you overlap and distort by the aliases with the other spectrum. So here is the signal of the DAC, the bottom light diagram. So the DAC is like processing the digital signal to the analog. If you have carefully like doing the sampling, have enough like bandwidth, you don't like have the aliasings. So we will have a copy of the signal of each Nyquist zone. If you're doing like undersampling, like when your signal is maybe like 5 gigahertz, yeah, but you sample like only like 2 gigahertz, we can use the higher Nyquist zone, and then you can save some like the sampling clock power and then your data converter capability. So what is the Nyquist zone mean? So for the data converter, we have separate the Nyquist zone by half of your sampling clock of your data converter. That is the FS/2. So we have like the Nyquist zone 1 is DC to the FS/2, and then second Nyquist zone is FS/2 to FS, and so on. And all the signal, if you have like carefully like doing the frequency panning, it can like fall back to the first Nyquist zone like correctly. Like for the diagram here, Nyquist zone 2, 3, and falling back to Nyquist zone 1. So like Nyquist zone 1 and 3, they are identical. 2 and 4 is identical, and 1 and 2 is like mirror each other. Like the 1 to 4, the highest frequency, and then falling back to the lower frequency to the Nyquist zone 1. That is some like the idea how we use the Nyquist zone. That means even though we know that aliasing is not desirable, but you can use these like features to use for our data converter, because we use the aliasing falling back to the first Nyquist zone to take the advantage, like convert the higher frequency to the lowest one. And then first we're talking about like the ADC frequency spectrum. So when we inject the frequency FF over in, and then the bandwidth is 1 times of bandwidth, and then at F in frequency, and then HD2 like the second harmonic is 2 times bandwidth of the input 2 times, and then the frequency is 2 times of F in. For the HD5 is 5 times wider than the input, and then the frequency is 5 times F in. You can see the harmonics, the amplitude is decreasing. Next, when we introduce the Nyquist frequency, like our sampling called FS/2, the signal will be fall back from the Nyquist zone 2 to the Nyquist zone 1, because the aliasing. That is the reason why the frequency panning is really important, because like the HD3 falling back, HD4 falling back, and HD5 is really close to our F-in. It depends on your filtering like capability and your spec of your SFDR. And then how to convert the frequency spectrum to the frequency panning. So as I said, like the F-in is 1x bandwidth, and then HD2 is 2 times bandwidth of the F-in, 3 times, HD3 is 3 times, and HD4 is 4 times. When we introduce the Nyquist frequency FS/2, the signal from if is larger than the first Nyquist zone, like the HD3, the second harmonic distortion will fall back to the first Nyquist zone, and then HD4 is larger than the second Nyquist zone, and then it will fall back to the first Nyquist zone 1, and then it will falling back. So the whole first Nyquist zone will be dominant by the HD4. So that is the reason why the frequency panning and higher sampling clock is take the advantage, because if you have wider sampling clock, and then your Nyquist zone will be bigger, and then you have more flexibility to avoid the distortion. That is the reason why we would like our Gen 1, Gen 2, Gen 3 will increase our sampling clock. So here is our like the RFSoC website in our Zynq.com. When you go to our website, it has like the documentation, like you can download our UG user guide and datasheet, and all the resource you can download like what they said. We have the evaluation tools, our analyzer, and then frequency panning. You can download it, and then you can like simulate around your use case. So when you download our like Zynq frequency panning, there is 4 major windows. The first one is the ADC frequency panning, and then we have the digital down convert DDC for the ADC, And then DAC, we have the DAC frequency panning, and then the DUC, digital up convert simulation tools. So here we will like present two cases for the 5G system. One is for the band 42, one is the band 79, 3.5 gig and 4.9 gig. So for the 3.5 gig carrier frequency, we set the sampling clock is 3.9 gig, and then the center frequency is 3.5 with the 200 megahertz signal bandwidth, and then the PLL we set is like 491.52 megahertz. So here is our signal. The blue color is our 3.5 gig with 200 megahertz. How come it down to 432? Because the frequency is come from the difference between the 3.9 gig minus the 3.5 gig. So the difference is 400 megahertz. So that is original from the second Nyquist zone and then fall back to the first one. Because I said they are mirror, right? So they will fall back to the lowest frequency. So here is our original signal. And then we have on our frequency panning spectrum, we show the PLL mixing. That is our clock reference to generate the distortion with your signal bandwidth. And then we show the XT2. XT2 is 2 times of your signal. So when we have like 400 megahertz, and then it will fall to the 800 megahertz, but the width, the bandwidth will be increased 2 times. So original, our signal is 200 megahertz, and then 2 times is 400 megahertz. So it's really close to our signal. And then HT3 as well. Our signal is 400 megahertz times 3 is 1.2 gig, and then our signal bandwidth will be 600. So that is the reason why we need to carefully doing your frequency panning and then sampling clock. We would like to avoid your signal overlap with the distortions component. Next, that is the DDC. So we want to see our signal after the NCO and decimations like processing, how the signal and distortion look like. So we're using the previous example, 3.9 gig sampling, 3.5 gig signal, and then our NCO, we want to put the signal on DC. So we put it negative frequency for 432 megahertz. So here is our signal on the DC. We can see the XT2, XT3 is close to our signal. So depends on your spec, right? So, and then one more thing is our decimation set 8 times lower. So our original light spectrum is like 3.9 gigs minus divided by 2. So our original signal is 1.9 gig, and then what we divide by 8 times, so our signal is only like 240 something megahertz. So the decimations at some kind of advantage. We want to limit your bandwidth and then save your digital resource for your other implementations and design. So that is the reason. Another reason our decimation is a filter. We want to help you to filter out the spurs and noise fall. That is 2 reasons why I would like to use the decimations processing. So and then we talk about the DAC. So DAC is similar, 3.9 gig, 3.5 gig signal, and then we can see our signal in the second Nyquist zone. If you want, because some customer want to implement their signal in the first Nyquist zone, what we can do, we can enlarge your Nyquist zone bandwidth, so we can increase your. You can increase your sampling clock. Original, we are 3.9 gig. When we increase the frequency up to 9.8, you can move your signal, original signal on the second Nyquist zone to the first Nyquist zone. That is some advantage because some customer want to work on the first Nyquist zone because have a bigger amplitude, and then maybe they have some consideration about the second Nyquist zone performance, like the linearity or distortion, something like that. So that is the reason why they want to do it on the first Nyquist zone. And then second case, after 3.5 gig, we would like to present, show it 4.9 gig. If we're doing like band 79 4.9 gig, if our sampling clock is only 2.2 gigahertz, you can see our signal is 200 megahertz wide and 4.9. Our signal is overlapped and hit by the HDV, the third harmonic. If your performance, if your sampling clock not large enough, so it depends on your spec, right? Our RFSoC, like our HDV spec, can be going down to 75 dBc. So if your spec can accept that kind of like performance, you can still use it. But if you want to have better like SFDR performance, you need to change your sample frequency from 2.2 to higher frequency like 4.4. If you have like 4.4 gigahertz sample length, so your bandwidth and your Nyquist Zone increase double it. You double your Nyquist Zone, and then you can see all the distortion HD2, HD3 is more far away. So you can like improve your FSDR, and then easier for you to do like frequency panning. You don't need to consider where it's coming from the spurt or like the unwanted signal coming into your wanted bandwidth. So that is the reason why we want to have higher sampling clock. And it can improve your FSDR performance, and you have more flexible on your frequency panning. Like our Gen 3, our DAC can sample up to 10 gig. So you have more freedom to play around your specific use case and design example. So do you have any questions about frequency panning? And then next topic, I will talk about the multiband. So for the multiband, why customer want to use multiband is because multiband support, you can just build single platform to cover all your different configurations like different carrier frequency and bandwidth. Like for the 5G, some customer maybe want to do like 3.5 band 42 gig, and then some platform you want to build 2.6 gig or 4.9 gig. So if we can support like multiband, you can only build one platform to cover all the frequency band for the 5G configurations without doing major surgery on your PCB design, pick the specific like bandpass filter or VGA filter, something like that. So here is traditional like the architecture like the super hybridized DAC, right? We need the JC204 communications, and then we need two individual paths to generate the band 1, maybe 3.5 gig, and band 2, 4.9 gig. So if you use our RFSoC, we have the multiband support. Our DAC, only one DAC, and then we have like two different DUC upconvert. One path you can generate like 3.5 gig with the NCO frequency, and then the other path we can set another NCO frequency at 4.9. So we can generate two different frequencies in the one single DAC platform. So like I said, if you're using traditional one, all your different band, you need to build one individual like PCB design. But if you want to do like single one platform, you can pick our RFSoC. So if you pick only one, you are more robust because you keep working on the same platform, right? If you find out the error, you don't need to like check an error the other platform. So that is another reason. So for our Gen 3, we have like CU43. We support like 4 interpolation like the Debug path, 4 of each DAC, and then we have like 2 for the ADC, and then 74, 78 we have support like 2 like individual like Debug for the DAC. So we would like to take investigations for the ADC like dual band DDC. So 2 signal coming in to our like 14-bit ADC. One NCO, we said we filter one band, and then other signal we filter another band. So you don't need like individual path for each single band, because so your end product and your application is more flexible, because when the signal coming in directly, you don't need to care which specific band you are like filtering and sampling. So here is our use case. I just picked the GPS. We have the frequency 1 and frequency 2 antenna coming in. We don't need to consider this band is only frequency 1 or frequency 2. We use the combined band pass filter for band 1 and band 2, and then go to the LNA. And then in our chip, we have the RF annulator, so that is our DSA. And then each ADC, we have both decimation path individually. So we can filter out the band 1 is 1.5 gig, and then our band 2 is 1.2 gig. So here is, I use our CCU111, our Gen 1 to do the multiband experiments. So here is our two signal, band 1 and band 2. Band 1 is 1.5 gig, and then our sampling clock is 1.9. So that is the reason why they falling back to 400 megahertz, and then the L2 is 1.2, and then our sampling clock is 1.9, and falling back to 700 megahertz. And then you can see a lot of the spurs is still okay up to 75 dB FS, and then our noise floor is about 95 dB FS. So we set our path. One is the ADC path set for the NCO1 and NCO2 for two different frequency settings. So for the L2 frequency, we set the negative 738 because we want to bring down to the DC. And then the decimation, we set 8. And then coming to our result, you can see the noise floor originally is from the 95, and then it's down to 105. So it has some filtering, and then our HD2 originally is 75, it's down to 80 dB FS. And then our signal is down to 0 megahertz. So that is the implementation. We filter out one signal. We can capture this signal to do the processing in our FPGA. And then similarly for the L1, we set the different NCO frequency, negative 391 and 8 times decimations. And then the signal is down to 0 megahertz, and then HD2 is 80 FS. And then the noise floor is 105 as well. So the filtering and then the processing is improved. And one more thing, you can see our frequency originally is 1.9. Right now it's only 122.88 because it's 8 times less. So you can save your resource for your other implementation on your FPGA. So we're talking about the multiband. We would like to highlight a little bit for the latency. For the Gen 1, the lower latency, we can support down to 25 nanoseconds. And then ADC is 47. Due to the higher sampling, our Gen 3, our latency can down to 20 nanoseconds. And then our ADC is from 47 down to 33 nanoseconds. So if your application really care about latency, our Gen 3 improve the latency as well because our sampling clock increased. So here is our summary from data set. Our RF Zynq is keep investing the RFSoC. We have Gen 1, Gen 2, Gen 3, and Gen 1, Gen 2 is in production. Gen 3 is in evaluations. If you want to take a look at it, you can go to our demo booth. We have our Gen 3 demonstrate our Gen 3 performance. And then we have a lot of the board and key support. And then our I would like to highlight that our Gen 1 CCU111 is selling really good because we are the only platform can characterize all the 5G performance. Because when you go to the analog data converter company to buy the evaluation board, you only either buy the ADC or DAC. But in our evaluation board, you can we can cover both ADC and DAC in 8x8 or 16x16 channel plus the FPGA. You can doing the whole 5G evaluation system. And then for my section, we would like to highlight that our RFSoC is truly enable the software-defined radio. You can change your configuration through the digital or software. You don't need to pay like physical doing the board design on the analog. We would like to make the digital dominant than the analog. So it's easier for you to do production and verifications. And then our Gen 3 higher the sampling cost, so it has to increase the frequency flexibility and then minimize the latency. And then multi-band, you can build one board for cover all your different configurations. And then the other advantage is lower system power and footprint because we don't need the JST204B interface. And then we have a lot of like resource and data you can download in our website to help you to do the design. So that's it for my presentation.